Hi all, hi again. Hope all of you are doing great at home, resting, being protected from the virus and all. So today we will look at a new topic in the list of topics of the module, which actually is not a very lengthy lecture today. It's on feedback. Now we've been talking about feedback a little bit when we were talking about the op amps, and we saw that we used negative feedback, and without actually discussing about the feedback theory as such. That's what we are going to do now. We discussed about the Smith triggers as well, and during that discussion we saw that the Smith triggers use positive feedback. Now the effect of negative and positive feedback, although we used both of those, were not properly discussed so far. So this is the point where we discussed that. So as I said, there are two types of feedback. One is negative, and the other is positive. So negative feedback is degenerative, which means that the effects are actually reduced, the gain would be reduced, which is used in amplifiers, as we saw in op amp amplifiers, because the op amp has a very large gain, theoretically infinite, but practically it was in the range of 200,000 odd. So we used negative feedback to compensate or reduce that uncontrollable gain or extremely large gain, at least to certain extent. So then positive feedback is regenerative feedback, which actually we used in oscillators. So we actually fed back certain component from the output to input in such a way that we wanted the A beta to be 1, and that actually continuously produced the output. So that is what we used in oscillators. So let's now look at the oscillator principle, or the basic transfer function of oscillators, the feedback. So we have the forward amplifier, right? So forward amplifier is there. A, and we have the output, right? So that's the output, V out, and we have the feedback network, beta. Let's say this is V out, and we have the summation point, either plus or minus. This is the adder, and let's label this as X out, and we get the feedback version or feedback version XF, and XE is the error, and this is our XI, or the input VI, right? So let's label using X's. This can either be positive or negative feedback, right? It may be positive, it may be negative. This is anyway positive, right? So if we have a positive sign in here, it is positive feedback. If it is negative, it is negative feedback, right? So in here, if it is if it is positive, means positive feedback, and if it is negative, it's negative feedback. in this block diagram, that sign positive being positive or negative gives you, now if this is negative, the feedback is combined with the input in a negative way, so it's negative feedback. If it is positive, it is positive way. Now let's check for the feedback gain. Feedback gain is x out over xi. Now xf is now a feedback is that we'll start from the basic. So xf is equal to beta into x out, and xe, the error is xi plus or minus xf. So plus if positive feedback is used, minus if negative feedback is used. Thirdly, we have x out equal to a xe. Right, now from all these three, let's try to find out x out. So from these three, x out is equal to a xe. A xe is xi plus xf. So xi plus or minus xf is beta x out. Right, so we can take x out in here. So x out is x out into 1 minus or plus. Now plus sign, when you take this to the other side, becomes minus, and minus becomes plus. So a beta equals to a xi. So the gain function af, the feedback gain, af is v out, or rather x out over xi, which is from this x out over xi is equal to a over 1 minus or plus a beta. So if it is positive feedback, for positive feedback, af is a 1 minus a beta, which is, as you can see here, it will become a larger value. So the gain will be increased, and in the case of negative feedback, for negative feedback, af is a over 1 plus a beta, because the sign swapped in here. For positive it is minus, for negative it is plus. So let's now in here 1 plus a beta is the amount of feedback. Loop gain is a beta, so it's actually the gain of the loop, right? So this is the loop, and loop gain is a beta. Now gain density is the derivative of af over a, which becomes, if you simply use the feedback gain, you see that it is 1 over a plus a beta dA over so gain sensitivity is or gain density, you can see that it is reduced by a factor of 1 plus a beta in here. It is in negative feedback, right? Then the bandwidth is actually expanded. Bandwidth is there, so that is a feature of negative feedback. So the gain actually will be reduced, and the bandwidth is expanded in the case of negative feedback, right? Now noise also will be reduced, or that noise content, signal to noise ratio is also better in the case of negative feedback. So many cases, many benefits are there when you are using negative feedback. Now this shows the gain profile, again saturation and so on and so forth. So as you can see here, the gain saturation will occur later when you have negative feedback than it happens earlier. So that is why op-amps we use negative feedback to control the nonlinearity or the quick saturation of the gain. Now when it comes to topologies, based on the connections that you have in the input and the output, basically you can have 4 different constructions. That is, you may have parallel input, as you can see here, or shunt input, which actually measures the output voltage. So in that case it is a voltage input. Now this in and out is in series with respect to the feedback network. So series in, shunt out, or we say voltage or voltage sampling in here, and in this case it is mixing. So let's talk about the output side. If you put it in on the output side of the amplifier, if you take that parallel into the feedback network, it is shunt, which means that you measure the voltage, so voltage in, and if you put it in series, that is so if you we'll take that a little out from here to make it simpler, easier. So if you now let's say you have this amplifier, right? If you connect it in parallel to the beta network, that's there, you this is your beta, A and beta, you measure the voltage. And if you actually connect it in series like this, whatever the direction is, then what you are measuring is, what you are sampling actually is the current going to the load, not the voltage. So this is voltage, and this is current, right? In the case of mixing, if you mix it, this is your amplifier, if you mix it parallelly, then what are you mixing? What you are mixing is a current. So you can apply KCL to this node. You are not mixing a voltage. So this is current mixing, this is voltage sampling, and this is current sampling. And if you connect it in series to the input, what we are now mixing is voltage. So voltage, so this is current mixing, right? Current mixing and voltage mixing. So as you can see here, like although we connect it in a similar way, in here we are measuring the voltage, but we are mixing current. On the right hand side, we are mixing, the connection is almost the same, but we are measuring the current to the load in this case, but mixing a voltage, because this voltage and that voltage is the addition that you see here. So combining these four, you have voltage sampling, voltage mixing, voltage sampling, current mixing, current sampling, voltage mixing, and current sampling, current mixing. Those are the four that we are looking at in here. So in this case, as you can see here, the input impedance is increased, right? You can show that it is okay. Let's look at the names first. Voltage mixing, voltage sampling. So voltage is mixed, voltage is sampled, and voltage is mixed. However, it is series shunt. So series in, shunt out, series in, shunt out, or series shunt. From the connections you can see that if you look into this, right, Ri, right, let's take that. So Ri, the resistance that you see is this plus this, so it is increased now. Right? You can prove from the techniques that we have already used, you can prove that it is the input resistance times 1 plus beta, because that is the feedback factor, 1 plus beta, right? And when it comes to the output resistance that is actually seen by the amplifier, now it is 2 in parallel, so it will be reduced. So this is R out feedback, that is parallel. There are 2 parallel resistors, the load was there and this is there. So now even if you look from here, there are 2 actually. I think this is RF, R out F is this. So when you look into that, it is actually reduced by a factor of 1 plus A beta, right? So that is for a voltage amplifier, voltage mixing, voltage sampling. Then you have the current amplifier, where you have current mixing, current sampling, or now in here you can see that it is the current that you actually measure, right? Current to the load is what is measured in the feedback network, and what is connected is actually a current. So current mixing, current sampling, this is mixing, this is sampling. However, it is series in, shunt out, or series shunt feedback. Now in this case also you can see that the input impedance is now reduced, so it is reduced by a factor of 1 plus A beta, and output resistance is now increased by a factor of A beta, right? So that is the current amplifier. Thirdly, you have transconductance amplifier, where it is a voltage mixing, current sampling. So input is current, voltage, output is a voltage for the feedback. So we call it as series input. Here you have a series input and a series output. So series in, series out, or series feedback. Now in both these cases you can see that the impedance or the resistance should increase by a factor of 1 plus A beta. So here it is increasing by a factor of A beta, here also it is increasing by a factor of A beta. Finally, you have the trans resistance amplifier, where input is a voltage and the output is a current, or current mixing, voltage sampling, or here it is shunt, here it is shunt. So shunt feedback, or shunt in, shunt out topology. In both these cases you can see that the impedance is, or the resistance input and output are reduced by a factor of A plus beta, because this and this are in parallel now, right? So now to prove these input and output resistances, what you may have to do is to find out the voltage and the current and divide the voltage by the current. Then you get these relationships easily, right? Try that at home. Now the effect of feedback on amplifiers: if the poles are located in the negative side, then it will actually decrement, the amplitude will be decrement, and that will be stabilized at 0. And if the poles are on the right hand side of the imaginary axis, then it will be increasing, and after some time the output will saturate. For sustainable amplification oscillation, you need the poles to be exactly on the imaginary axis, so J component to be real component to be 0, right? So exactly the poles are on the imaginary axis, right? So that will give you proper amplification. Now if you look at the gain bandwidth expansion. If you plot the board plot, as you can see in here, in this case at omega p, the gain is omega a naught. So if you draw the board plot at omega p, it will start going down at a 20 dB per decade ramp. So in this case, the feedback gain, as we derived earlier in an earlier slide, the gain is now reduced by a factor of 1 plus a beta. So the gain is now less, and in the meantime the bandwidth is also, or the pole location is also has gone up by a factor of 1 plus a beta, right? So that is the feature of the negative feedback in amplifiers. So when the moment that you use negative feedback, the gain reduces, and in the meantime the cutoff frequency or the bandwidth increases by a factor of 1 plus a beta. Now let's use this knowledge to find the gain of an amplifier, op-amp amplifier, right? So we've been deriving this amplification or the gain of an op-amp amplifier using the fundamental theory, but here we will try to do that using feedback theory. This is for the inverting amplifier. So let's label this as inverting amplifier gain using feedback, right? So you have the amplifier plus and minus, plus, sorry, this is minus, right? Minus plus, go down, so Vi, right? Let's start with the okay, let's try this out. Okay. Right, RF. Now okay, this is V out, and we know that this is VE, right? Now from the let's start with the non-inverting amplifier. I guess that will be easier, right? Non-inverting. For non-inverting amplifier, so this is minus, this is plus. Right, now the feedback network beta, let's take out beta, is the two resistors, comprised of the two resistors R and RF. So this is V out, and this is VF, right? That's what we want, right? Feedback voltage. Now what is VF? R over R plus RF, V out, right? this will give us beta equal to R over R plus RF, right? That's the beta factor. Now for this here we have negative feedback, as we have negative feedback. A feedback is A over 1 plus A beta. So A over A is the gain of the amplifier, A over 1 plus A beta is R over R plus RF. So if we simplify this, AF is equal to A over R plus RF divided by R plus RF plus AR, right? So that's our feedback gain. This is what we have already derived. Now if A is infinite, right, now we have to manipulate the gain function a little bit. This is for the ideal op amp. AF is equal to, we'll divide everything by R, so R plus by A, R plus RF divided by R here plus R plus RF over A, and this A goes to infinity. This A is infinite. Now moment that A is infinite, this term becomes 0, so this becomes R plus RF over R, so it is 1 plus RF over R, right? So this is what we actually got from the fundamentals. Now let's check for the inverting amplifier. What would that be? For inverting amplifier, so what we need to find here is VF, the feedback voltage, over V, right? VF over V. Now what do we have as VF over V in this case, in the case of an inverting amplifier? Let's check. So for the inverting amplifier, what you have is the amplifier is there, minus plus, this is grounded, and you have a resistor here and a resistor here, right? So this is your VI, this is your V out, RF over R. Now here what is actually beta, right? In this case it is little bit difficult for us to manipulate like what we did in the non-inverting amplifier, because we actually can't extract a full beta circuit. This is actually our VF, right? So what we need to do is to find out what VF is. So in here what we have actually is, we have some resistor division, right? This is our VF, right? This is RF, we have V out, this is, let's see if it works, R, this is VF. So VF is equal to actually the voltage divided version of V out and VI, right? So that's actually R over R plus RF times V out minus Vi plus Vi, right? So that's Vf, right? Now that makes it little difficult, right? So let's forget about that one, right? So let's stick ourselves with the non-inverting amplifier. I'll work this out later on, and I'll upload an update of how we can use feedback theory to derive the gain of the inverting amplifier little later on, right? So this was actually we did earlier for the inverting amplifier, and we got this result with the longer route. However, we actually come up with an easier way using the feedback theory. So you can use feedback theory in future if you want to work with circuits, op-amp circuits basically. So what you need to find out is what is A and what is beta, and whether you are using negative feedback or positive feedback. So it will be, if it is positive feedback, it will be AF equal to A over 1 plus beta, 1 minus beta, A beta, and if it is negative feedback, it is AF equal to A over 1 plus beta. So I'll work out this one and upload an update later on. Till then, we'll catch you or leave at this point, and we'll regularly post the lecture updates. If you have any doubts, any clarifications needed, you may contact me or Suba, either of us, through the WhatsApp contacts that we have shared already. Alright, work from home, stay safe, work hard. See you next time.